Okay, so now we have Oscar the puppy. So Oscar the puppy has a uniform beam on which he likes to walk back and forth. The beam has a length of 20 meters and a mass of 60 kilograms, and it's supported on these 2 points A and B. Oscar's a growing puppy, and soon when he stands over here, the beam will tip. What is the maximum mass that Oscar can have and still frolic to the end of the beam as shown below without tipping it? And Marvin kindly gave us the answer, so we'll be able to check our work. Okay, so here we have an extended object, we have a bunch of forces on it, and we're asking about tipping. So you should be thinking forces and torques, right? So this is a we want to know how heavy can Oscar be and have this thing still not tip. So in other words, have it stay in static equilibrium. So we know in static equilibrium, the sum of the forces has to be 0 and the net torque has to be 0. So let's start by just drawing all the forces that are acting on this object. So the object we're interested in the tipping of is this plank. So let's draw all the forces acting on the plank. So there's 3 things touching the plank. There's this triangle A, so pivot A, so that'll exert a force up. So this is the force from support A. And support B is touching the plank also. Oscar is sitting on the plank. Gravity is pulling on Oscar, so Oscar is exerting a force on the plank that's equal to his weight. So this is the force of Oscar. And so that's all the contact forces, and gravity is also acting on the plank as a long-range force. So gravity is going to act at the center of mass of the plank. So find roughly the middle of the plank. The force of gravity is going to act at the plank right at that point. Okay, so now we could sum the forces, but usually when I'm doing a statics problem, I will do the torque equation first, because sometimes that's the only one you need. So I'm going to start by sorting out the torque. So if we look at our equation sheet, let's go to the section on torque. So here we go, torque. So this tells us how to calculate the torque from a force. So you want the distance from the pivot, so you have to remember to pick a pivot, and you want to multiply that by the force that's perpendicular to the lever arm. So you can think about that in either of these 3 ways. I usually use these 2 instead of this one. So let's just write that down so we don't forget. So a torque exerted by a force F is, let's say, R times the force that's perpendicular to the lever arm. Okay, so we need to pick a pivot, and we need to figure out what our lever arm lengths are if we're going to sum up all the torques. So when I look at this, I need to pick a pivot, and I want to pick the easiest pivot that I can. So if there is a physical pivot, I will usually try to pick that as my mathematical pivot first. So once Oscar starts to tip this beam, the beam's going to rotate around this little support, which means that this end is going to lift up. So if the stick tips, then this force is going to go to 0. because if the beam loses contact with A, there's no longer a contact force. So this is very much like the cow tipping problem or the Marvin problem from, I think it was practice exam. It was practice exam 2 or 3, had the thing with the 2 strings. This is very similar to that problem. So this will go to 0. I want to pick this as my regular pivot. So now I need to figure out the distances to this force and this force, which are the only two that are going to contribute to the torque. This is at the pivot, so it's not going to contribute to the torque because the lever arm is 0. Okay, so sum the torque, set that equal to 0. So this is our pivot. We're going to have the torque due to Oscar, and we're going to have to add the torque due to the weight of the beam. So the torque due to the gravitational force. This force is 0, so it's not going to exert a torque, and this one again is at r equals 0, so the torque will be 0. So that has to be equal to 0. Okay, so if we look at Oscar, how far is Oscar from the pivot? Well, it looks like, so this is 3 meters. This is 13 meters. That's a total of 16. And they told us that the total length of the plank is 20. So that means that this distance, r, is 4 meters, because it's 16 minus 13 minus 3. And if we want the distance, if this is 4 meters, and this is the center of the beam, this whole distance is 10 meters, which means that this distance has to be 6 meters. Okay, so Oscar's torque is going to be the force of Oscar times the 4 meters. And is Oscar's torque going to be positive or negative? Well, if we say that clockwise is negative and counterclockwise is positive, this will rotate, Oscar will rotate the plank clockwise, so that will be a negative torque. The gravitational force is trying to rotate around the pivot counterclockwise, so that should be a positive torque. So the distance of 6 meters, and we want the force of gravity. And these are already perpendicular to the lever arm, so I didn't have much trouble sorting out the torque for these two. So this is negative 4 meters times the force of Oscar, which is his mass, so the mass of Oscar times g. And we're going to add the 6 meters times the force of gravity on the plank, which is the mass of the plank, times g. So these g's cancel out, and actually the units of meters cancel out. So we have minus 4 mass of Oscar plus 6 times the mass of the plank equals 0. And if we want Oscar's maximum mass, we're just going to solve for that. So that'll be the mass of Oscar is 6 times the mass of the plank divided by 4, which is equal to 1.5 times the mass of the plank, which is 60 kilograms. Which gives 1.5 times 60 is 90 kilograms. So our answer agrees with Marvin.